Good afternoon. This is the topic 12 from the IB diploma. This is a high-level class. We're going to look at the induced electromotive force, and first of all we'll do an introduction to this. Okay, we'll do a recap. If you remember that from your fields and forces topic, that when we have a current carrying wire like this, so the current is going from left to right. We're going to place it in a magnetic field. The magnetic field is going into the board, so the magnetic field is going in to all areas here. What will happen to the wire? So we have a current carrying wire in a magnetic field. There will be a force. You can try to figure out now, using Fleming's left-hand motor rule, which way that current carrier will travel. And the answer is, it will go up. First finger into field, second finger to the current, third finger, the thumb rather, will push the current carrying wire upwards. So what do we find out here is that if we have an electric current, then we know the electric current produces its own magnetic field. And if we have this electric current, and if we have an electric current in another magnetic field, the two magnetic fields will interact and create a force. And if we have a force, this electric current can make movement. So this is the whole principle behind it. We have basically what's called a motor, an electric motor. The principle is an electric current can be used to provide movement. See what happens if we get movement. Can we get electricity from movement? And what you have is a coil of wire connected to a voltmeter or an ammeter, so that will measure the current or the voltage. You move the magnet into the coil, move the magnet out of the coil, reverse the magnet, have the south going into the coil, have the south coming into the coil, change the speed of motion, make it go faster, make it go slower. Change the strength of the magnet, have two magnets together, find a bigger magnet. Change the number of coils. Instead of having 200 turns, you could have 400 turns or 600 turns of wire. You could try spinning the magnet round like this to see if that has an effect. That's not so easy to do. Try moving the coil towards the magnet instead of the reverse. Instead of moving the magnet into the coil, move the coil towards the magnet. And this is basically what you need to investigate. The results will be as follows. If the magnet is still with respect to the coil, there is no motion, there will be no voltage and no current on this voltmeter. There will be no voltage here. If the south moves in, then you will get a reading one way. If the north goes in, you will get a reading the other way. So you will get some current which will appear in the coil if the magnet is moving in or is moving out. What happens if you make it faster? Well, since the magnet is moving faster, the current which appears in the coil will be greater. If we move the magnet out, we get a deflection in the other direction. If we move it out faster, we get an even greater deflection in the other direction. If we move the coil towards the magnet, we'd get the same as if the magnet is going into the coil. It's the same thing. So, the conclusion from this experiment. When there is relative motion between a magnet and a coil, you will get an induced potential difference, or an EMF produced in the coil. If you reverse the movement and move it out, the EMF is reversed. It will be a negative EMF. If you increase the strength of the magnetic field, then the EMF is increased. If you make a stronger magnet, then the induced voltage, the induced EMF will be increased. So basically, we find that the EMF, the electromotive force, the induced voltage, is proportional to the rate of change of magnetic field. It depends how quickly the magnetic field is changing. How can we change the rate of change of magnetic field? One is the magnetic field strength. If we have a greater field strength, then it will change more. If we move the magnet faster, the magnetic field is actually changing at a greater rate, so that will have a greater EMF. If we have more coils of wire, each coil of wire will link some of the magnetic field. So the more coils of wire, the more magnetic field will be linked by the coil, which means if it's changing, a greater flux linkage, a greater linkage of magnetic field is changing. So here I have a problem. Try to solve this one. The magnet is moving into the coil and it diverts by 8 units, goes to the right. What happens if you repeat it with the south pole going in at twice the previous speed?